Thanks to the organizers for putting this together and for allowing me to speak, even though I'm not one of Alex's students. And I'm kind of a surrogate student, though, because I learned Schubert Calculus from Dominic, so I'm sort of like a grandchild in a sense. So what I'm going to be talking about today is all joint work with my amazing collaborator, Nantel Bergeron, and we'd like to thank our sponsors who've been giving us money to fly back and forth, and apologies to Greta Thunberg for all the flights between Toronto and LA. So most of the background of this, you guys have been, it's all been done in the last few talks, so maybe we can get to lunch early. That's the hope. What I'm going to be talking about, what I'm interested in studying, are these numbers that we keep seeing, C, U, V, W. And I'm going to keep indexing them consistently. U and V are the guys at the bottom. W is the one at the top. These are the Schubert classes in the cohomology ring for the flag manifold. And we want to know what their structure constants are. We know that they count things, so they're positive integers. And I want a formula for them. And I'm going to be specific about the type of formula. Nantel and Frank told me what to look for. Here's what they wrote. It remains an open problem to give a bijective formula for these constants. We expect such a formula will have the form saturated chains in the Bruhat order on S infinity from U to W satisfying some condition imposed by V. So maybe this isn't a conjecture, but because it's not specific enough for that. But it's got all the right intuition and all the right ideas, and it tells us a place to look. So you know what S infinity is. Anna told us that's when it's Sn, but n's big, right? It's infinity. So I just don't care about my permutations being too small and kind of sweep that under the rug. And why look for this kind of formula? Well, there are lots of reasons, and maybe Frank could explain them all to you. And I want to say, though, that there are so many different formulas that maybe we could find out there. And we've seen so much beautiful combinatorics just in the last few days. And I don't mean to eschew any of it. I'm going to do something very specific. I'm going to take the combinatorics that appeals to me, that gave me the most traction, that I made the most progress with. But that's not to say you shouldn't use all the other combinatorics that we've seen. And in fact, you should. Because I think all of these insights and advances that we make on a problem come when different people with different ideas, different perspectives, come at the problem from a completely different direction with different preconceived notions, and that's how we kind of get through together. So you should embrace all the combinatorics that we've seen. I'm going to be, again, very specific in the types that I'm pigeonholing in on. But before I pigeonholed, I actually did try out lots of different things, and I still don't quite get Mondrian tableau, but I'm really intrigued by them. But I've tried out lots of other things, and this is the part that I could understand. So this is why I chose this one. It's a very personal choice, and I'm not suggesting you make that choice too. In fact, I may be saying, don't make that choice, do something different, and let's go together down this journey. Okay, so this is the problem. Bruhat order. We also saw this, and Frank talked a lot about this. Here's a definition. So it's going to be the transitive closure of these cover relations. So how do you go up? You have a permutation, and you switch two numbers. So here, I'm switching the 3 and the 5. When is that an okay switch? Well, 3 has to be smaller than and left of 5. That checks out. And I want the number of inversions, the number of out-of-order pairs, to go up by 1, which means the number 4 had better not be in between them, and it's not. So that's going up. Take the transitive closure, that's Bruhat order. I want to think about it graphically. Why? Because I frankly can't deal with all these numbers. So I like pictures. They make me happier. And so I draw it as a picture. We've seen this. This is the Roth diagram. Colleen drew these for us. Now, in my mind, Colleen did them upside down. So you'll have to kind of stand on your head for the rest of this talk. But this is, I'm using coordinate notation instead of matrix notation. Why? I don't know. I actually don't have a good reason for this, but it's stuck with me now, and I can't switch. So I apologize for that, but like eventually maybe I can switch. But right now, I can't. So this is the permutation. I've written here the permutation U. I put the dot here in row 1, or sorry, column 1, column 3, column 6, column 2, and so on. Now, what's Bruhat order in this picture land? Well, I picked 2 dots where the bottom one is left of the upper one. That's this condition. R is less than S. I respect the alphabet whenever possible. And UR is less than US. Okay? So, and I'm going to switch them, but what's this condition? This says that if I draw this red box, I didn't want to clutter up my diagram, so I drew it below. If I draw that red box, there's no other dot in that box. Okay? That's saying the 4 is not there. Okay? And now, the bubbles matter So why are they bubbles and not boxes? Because when you draw boxes, we saw this in Jim Ping's talk, then you kind of have to say which box is a box and which one's just surrounded by boxes. So that's why I made them bubbles. Also, if you read Konert's thesis, he's talking about like champagne, and the bubbles are bubbles, and so they're bubbles. So bubbles. I color the bubbles. Why do I color them this way? The colors don't really matter. I just don't want to put numbers in the bubbles all the time, and so I follow the rainbow. So if you ever want to know what my color scheme is, my daughter did it to my notebook once, and instead of getting upset, I embraced it. This will be purple, blue, green, yellow, orange, red, pink. I don't know why pink's at the top. So that's all. But I somehow discriminate between this bubble, which is up in the top row, and the other bubbles that are in the middle. Okay? And I think of this bubble, and this is important, as dropping down to this row. Okay? And then I think of these bubbles as shifting left to avoid the death rays, because you don't want to pop the bubbles. And then the new bubble is a box. Okay? And I put a 1 in it because it's the first box that I got. I'm going to be looking at saturated chains, because that's what Nantella and Frank told us to do, look at saturated chains. So there's going to be more boxes. And I argue that this is a good model, not the good model, for what a skew permutation diagram should be. Okay, it's the analog of skew tableau. So any questions on how we're removing bubbles, adding boxes? Okay, so there's another equivalent characterization of Bruhat order. Okay, Bruhat order, what does it mean? Well, you compare two permutations in Bruhat order if for any choice of reduced word for W, I have a favorite, I'll tell you in a sec. Any choice, there is a reduced subword that's a word for U. That's Bruhat order. So that's in Bjorner and Brinty. You can read nice proofs of that. So what's my favorite one? I call it the super Yamanuchi word, but I didn't invent this. I just like this word. I don't know why I like that adjective. I need to describe this one. It's the top pipe dream. It's the word that has the highest reduced compatible sequence, right? It's the one that everyone has already seen that you sort of start with, okay? And how do you get it? Well, I get it by starting in row 6. I start numbering my bubbles 6, 7, 8, 9, 10. In row 3, I start numbering the bubbles 3, 4, 5, 6, 7, 8, 9, 10, and so on. And then I read it like a book. Maybe that's why I do it in this notation, because then I can read it like a book. We'll pretend that was it. So 6, 7, 5, 3, 4, 2 is a reduced word for U. Okay? And similarly, this is a reduced word for W. But let's pay attention to the bubbles in the boxes. So I got those boxes by taking a saturated chain from U to W. They're different saturated chains. They'll give you different configurations of boxes. Sometimes the same, but sometimes different. If I do the same thing and then I just don't read the boxes, that is the subword for U. That's why I think it's a skew diagram. That's why I think it's a decent model. I think there's some interesting combinatorics yet to be developed here. And Nantella and I kind of got lost for a month in developing some of this, and there's so many questions, and they're so interesting, especially in the K-Bruhat order, like in a minute that comes up, like trying to see this. It's fascinating. We're not going down that road yet, because we're going somewhere else, but I think it's an interesting thing to explore. So this is my justification for drawing these pictures. Okay, it's a skew diagram in some kind of natural sense. Of course, you could do other things. Okay, so these are the sorts of objects. When I say a saturated chain, this is what's in my head. So part of my talk is to tell you what's going on in my head, scary as that is, when I'm doing all of this stuff. So this is, in my head, this is what I see when somebody tells me there's a saturated chain. Okay? Okay, so what is the K-Bruhat order? So this comes from Monk's rule. If we've seen Monk's rule, and I think you guys saw it in the week before probably, but in Monk's rule, you can think about the terms that appear when you multiply a Schubert polynomial by a box, or sorry, a Schubert polynomial by a box, okay? And they have this K parameter that matters. So before you object, Frank, I really do think that this is a fair statement to call this a theorem. Yeah, but because see, I was vague, but we'll get to it at the end. But it's a theorem that Bergeron and Steele have in that same paper, that the formula exists of the flavor they wanted when you multiply a Schubert polynomial by a Schur polynomial. So here, V has to be K Grassmannian, which means that you don't have a descent unless you're at position K. All right? And in that case, you're multiplying by a Schur polynomial. Okay? And here the K matters, so what are all these words over here in red? I'll define them. K Bruhat order means you go up in Bruhat order, but R and S straddle K. So your lower dot's below row K, weakly below row K, and your upper dot's above row K. Or if you think about it in the way that Monk did it in his paper, he actually did draw like a vertical line in the one-line notation of the permutation and say you're switching across the line. So even he, who was doing everything geometrically, liked combinatorics. Okay, so that's K Bruhat order. And what's the weight of a chain? Okay, so this is what Bergeron and Satil defined. When you take this chain, what you do is you think about what's the big number that swapped down every time. Okay, so I switched the 5 and the 3, I think 5. That's my big number, and I write it above that step in the chain. So suppose I had a chain that went like this, and I've just written the big numbers. What's the weight of that chain? So I just don't like descent sets, so I use compositions instead. And it's equivalent, but you look where the descents are, and you say, okay, well, how many letters do you have here? There are 3, so there's a 3. And here's 3, so there's a 3, and there's 1, so there's a 1. This example is a partition, but it didn't have to be. It's just going to be a composition. And so we've seen Gessel's fundamental quasi-symmetric functions making appearances in several talks. And Frank and Nantel defined this guy. The input is U, W, and K. U has to be less than W in K Bruhat order. They take the generating function over saturated chains. To each saturated chain, they associate a Gessel fundamental using this composition theorem that is a symmetric function. It's Schur positive, and they prove that the Schur coefficients are these magical numbers that we really want to count. So they took this very geometric problem and they just knocked it into symmetric function land, where we have so many more tools and everything to solve these sorts of problems. So why do I call this a theorem that you have this thing? Well, in theory, one can group, since it's Schur positive, and these are positive numbers, one can group these fundamentals into Schur positive equivalence classes, and each equivalence class for the partition nu will have one chain of weight nu, and that is the sum condition. The magical regrouping, pick out that thing. That's the sum condition. It's not specific. So this is technically true, and a formula like this does exist, but we really would like this to be not vague. And it's still vague, but it's still a powerful reinforcement of this idea of the type of formula that one can look for. So that's the K Bruhat order. And I will say that as I think about chains in K Bruhat order, I think about them graphically in terms of those skew diagrams. But here's a question, and Frank, correct me if I'm wrong, but I believe this is open. Is it known which subwords of W correspond to a chain in K Bruhat order? Now I would like us to, globally. I think that would be really interesting. And some people have done some work on the universal Bruhat order, and it still didn't seem to come up there. So I don't know that people have thought of that. And I think it'd be really interesting which subwords correspond to the chains in K Bruhat order. Because you can get from U to W going outside the K Bruhat order or staying inside in a lot of cases. And I want the ones that stay inside. So I don't know how to do that. Okay, K Bruhat. So if given U and W, where U is less than or equal to W in K Bruhat order, fix, say, the super Yamanuchi word for W, which subwords of that are words for U correspond to chains in the K Bruhat order? I've given a way to correspond a subword to a chain by the way that I'm rendering these permutation tableau, these skew diagrams, and I'm wondering, not all of them are good chains. They don't all come from K Bruhat order. Which ones do? Can we tell? And our initial investigation seems like there was a lot of structure and a lot of patterns there, but we didn't finish that rabbit hole. Okay. So K Bruhat order, that one's important. And there's an answer, but it's not finished. Okay, so I think of chains like this. This is a chain to me. I draw these skew permutation tableau. I actually only have to tell you this one because you can back the whole thing out. Why? Because I put numbers in the boxes. Now, what are the numbers in the boxes? They tell me the steps that I took. As long as I have an ascent I keep the same number in the box. Once I hit a descent, I make the number bigger. That way I can tell if I had an ascent or a descent, and that way I know uniquely how to reverse out the chain. If you just give me this, it uniquely describes the chain. It carries all that information in it in a compact way, and that way I don't have to write the chain and all the permutations. I've got it all there. So again, it's a convenience tool for me. It's not strictly necessary. It doesn't change the information that I'm getting. It just helps me to see it all in a compact way. Okay, so I put out a preprint, and I had a conjecture for specifically that sum condition, right? That sum condition that we're missing in the Bergeron-Cecile theorem. I put a paper out, and I said what the condition was. Okay, and as many of you pointed out, okay, there's a counterexample. Specifically, this is a counterexample to the way that was stated. So I'm not going to tell you the way it was stated in that paper, but you can go look. The archive never forgets. I will tell you the way that it should have been stated. and you'll see that it's not nice. I mean, it's nicer because at least it's right, but it's not nice for reasons that you'll see. But it does work. This rule, as stated in that paper in the nice way, that's broken, actually does work in special cases. Yeah. I can. Oh no, it's not at all obvious. That's why this is THM, which stands for theorem. It's not clear that it's not clear from the definition that it's symmetric. It's clear that it's quasi-symmetric. Right, and that's why I think of these things as skewed diagrams, because everything that you guys were doing was sort of saying the same, like it was the same paradigm. But the sure positivity is much deeper. But the floor cracked. Okay, so which cases does it work in? It works if you're a hook, if the partition nu, remember we're multiplying by a sure polynomial as a hook, which if you want, it's a permutation that looks like that. Or if the Schur polynomial has more variables, or at least as many variables as the Schubert polynomial. So let's look at those special cases. And also, why special cases? So everybody's been doing special cases all week. And why do we do special cases? Well, first of all, because we can. And the general case is generally hard. So we start wherever we can get traction. But it's not just that. You want to do the case where it gives you some kind of new insight to get to the next thing, to kind of open it up, right? So there's an iceberg, and we can just see like the Littlewood-Richardson rule, and there's all of this stuff below it that we cannot understand, or at least I cannot understand. I won't speak for other people in this room. I don't understand it, but if I could just see a little deeper, then maybe I would get it. Maybe I could see the whole thing, right? And so that's what we're looking for. When we do these special cases, we're looking for a case that kind of cracks it and is like, oh, that's why it's different. That was that thing I didn't see because what I was doing before was too special, and now I see better. So that's sort of what I'm trying to do with the cases that I look at. Also, we should listen to David Hilbert. So, special cases. So really, they're two, but kind of they're four. So let's just go back in time for a minute. I won't make us late for lunch, I promise. So Littlewood-Richardson stated the Littlewood-Richardson rule. It's theorem 3 in their paper. And right below theorem 3, it says, we don't actually know a proof, but we can do it in the case when the second one's an H. I'm not sure the context in which they were using the word theorem, but they did prove it for the Pieri case. But they stated it beautifully, and they stated it just like this. Again, there are other ways to state the Littlewood-Richardson rule. I believe that probably at least 50% of the people in this room have proved the Littlewood-Richardson rule their own way and have a slightly nuanced way of describing those coefficients. So I'm not saying this is the only way. I'm just saying that Littlewood-Richardson proved that, well, asserted that the type of formula we're looking for does exist in this case. So Robinson gave a proof with cavernous gaps. And it's really hard to read his proof, not because it's 80 years old, but it's just incredibly technical and terse. And it's funny that I say that, but it's incredibly terse, and there are big gaps that weren't noticed right away. Shinstead was really a computer scientist, and he wasn't interested in this rule. He was looking at longest increasing subsequences of a word. Okay, so computer scientists get a plus plus and a plus plus here too. So Shinstead was looking at that in 1961 and came up with this insertion, which actually has the exact same flavor of the work that Robinson had done. And then Don Knuth just generalized the hell out of it. We have Knuth equivalences and all this stuff. And then Thomas put these ideas of RS and K together and gave a beautiful bijective proof of the Littlewood-Richardson rule. And again, is that the only proof? Of course not. Half the people in this room have their own proofs. But it was the first proof. And there's something nice about it and really elegant about it. It's a bijective proof. It's sort of a really, really nice one in my view. There are certainly things you can't get from it. I believe you cannot prove saturation using this rule. I believe you cannot see certain symmetries. Actually, you can't see the symmetry between mu and nu. And we know that multiplication is commutative, and you cannot see it from this rule. So it's not perfect, but it's amazing. Okay, well, the rule that I stated is a generalization of this. It specializes down in that case. The skew objects become skew objects that you're familiar with. So we have Monk's rule, too. So again, Monk's rule, I sort of mentioned it before. It's where you multiply by a box, which is a simple transposition. And it's 0 or 1. It's 1 when you go up in K-Broha order. It's 0 otherwise. So Monk proved it geometrically. There are lots of nice proofs of Monk's rule. Maybe, I don't know, a third of the people in the room have proved Monk's rule. I don't know. Maybe it's still half. My favorite proof is due to Nantel and Sarah. They do an insertion algorithm on pipe dreams. And it's the flavor of proof of this. And it's not just the flavor. Literally, when K is super big, it reduces to RSK. Like, it's the same structure. So it's a really nice generalization. And it's I don't know, it takes you guys like half a page to prove it. It's so short and so elegant. But it doesn't work with the bumping lemma. Shinstead's amazing bumping lemma that says, like, oh, if you keep inserting things that are increasing, then you get these strips. It doesn't hold. It's not that they couldn't prove it. It's actually false. So that was disappointing, but that's okay, because even not being able to do that, they noticed from computer experiments that there was a really nice statement of Pierre's rule that they could make. So they conjectured in this paper Pierre rule in a very nice form that Frank proved geometrically, and then Frank gives like 4 different ways to think of the rule that are equivalent in terms of these chains. Like, you can think of it as you're never doing things in the same column, or you're doing it in, like, right to left, and there are different ways of thinking about it. And there is also a combinatorial proof of this due to Kogan and Kumar, who sort of hacked the Bergeron-Billy insertion and sort of just broke it a little bit just to force the row bumping lemma to work, but you can't do multiple rows. So they did get it to work to prove the Pierre case, which is amazing, but it somehow, when you do that hack, you break the ability to generalize it and keep going. And I should say this also does hooks, because somehow, like, rows, columns, it's just hooks. So then there's Kogan's rule. So Kogan noticed that the Bergeron-Billy insertion does satisfy the bumping lemma when K is huge. And he used that fact, it's a theorem, but he used that to come up with this theorem. So I want to look at the statement of this for a second. So I find this a slightly unsatisfying statement, okay? So it's awesome, but also slightly unsatisfying. So he switches W and U, which is kind of annoying, but roll with it for a second. So this is the smaller one, is a permutation that satisfies 1, which means that you're multiplying by a Schur polynomial that has at least as many variables. That's the Kogan case, okay? Lots of variables in your Schur polynomial. In other words, K is huge, okay? And pick any pipe dream, RC graph, U, okay, that's in your target, where you're trying to get to, so the big one. And then do Bergeron-Billy insertion, right? So R is a pipe dream for your small guy, and you Bergeron-Billy insert a tableau, because you turn a tableau into a word, because that's what RSK does. It turns a tableau into a word. So then you just insert that word using Bergeron-Billy insertion into the pipe dream, and you see how many times you get U. So literally, if I wanted you to actually compute one of these Littlewood-Richardson numbers using this rule, what you would have to do is construct all the pipe dreams and do a whole bunch of insertion. And that's the sense in which I find this unsatisfying. It's theoretically beautiful, but it's a little tricky to work with. And if you think this is bad, just wait. But you see the limitations of it. It's somehow like, couldn't they have said it better? And in fact, that's one thing that the rule, the incorrect rule, which does work in this case, is nicer as a statement, perhaps, it's equivalent to this where you're picking a very specific RC graph, the top one, okay? The one where it's the Roth diagram. And when you pick that one, then you exactly get that the number of things you get, the number of these pairs is going to be counted by these permutation tableau. So in that sense, I feel like, okay, well, it kind of cleans up this statement in a way that was somewhat unsatisfying for me. So now you don't actually have to do the insertion, you can just, you know what the recording tableau look like. Okay, so those are the special cases. Questions? Okay. So now I want to talk about, well, this is one of these weird things where I have to give you the proof before I can give you the statement of the theorem. So bear with me here. I just love Conant's rule. I had worked with RC graphs and pipe dreams with Dominic, and then he told me Conant's rule one day in my office, and then I pretty much never drew another pipe dream again. I don't know why. It's so awesome to me. I am obsessed with this rule. I just really, really like it. And it's a personal preference thing, and I'm not saying you have to love it. I think you should, but you don't have to. And again, using different models is fine. It seemed like not a lot of people really embrace this model, but I certainly did. So again, I'm trying to solve this problem. I'm now using Schubert polynomials, right? I'm not in the flag manifold anymore. I'm just using honest-to-God polynomials. Notice they haven't come up before now. Before now, I didn't actually need to talk about them. It's only when we get into the gritty of the proof, but the statement doesn't need them. Okay, so Schubert polynomials are the generating polynomials for Conant diagrams. And what's a Conant diagram? You start with the Roth diagram, okay? And then you take any row you want, and you push the rightmost bubble in that row down. So I could push this bubble down, I could push this bubble down, I could push this bubble down, I could push this bubble down. And then you repeat. And all the diagrams you can get from doing any sequence of those moves in any order that you like, the set of diagrams, the multiplicity-free set of diagrams you can get, are the Conant diagrams. It's really kind of fun and nice to do it. And that's it. So I'm not going to go into, I limited myself to only a few slides, so I'm not going to explain Conant's rule more than that. Just know that it's there, it exists, it's awesome. And the weight we just get by taking, this would be, there's no x1s, we get an x2, x3 cubed, no x4, x5, x6 squared would be the monomial associated to this one. And by the way, just from Jianping's talk to harken back, how do we know this is the leading term for the Schubert polynomial? Because you push the bubbles down. And Colleen has a conjecture for in the K-theory version, which is you push the bubbles down and sometimes you also left it, right? So then you can kind of see the top degree terms would follow easily from that. Okay, so the proof that I'm looking for, right, before I get a rule, the proof of the rule that's in my mind, the dream, is, do what? Oh, a different Colleen R. Sorry, Colleen. Thanks. So Alex and Colleen Ross have a conjecture. Thanks. I think I did get you guys mixed up in my head. Sorry. But anyway, the conjecture is still open, right? And it's the right. It just feels like the right conjecture. I mean, it just looks so perfectly K-theoretic and Conant. Okay, so the proof I'm looking for the statement that we don't know is the set of Conant diagrams times the set of Conant diagrams must be in bijection using some kind of RSK-like insertion with the set of Conant diagrams for this guy and the objects that this set will count. These, if we went to all Grossmanian, all K-Grossmanian, this would be tableau times tableau is insertion tableau, recording tableau. The recording tableau is a Littlewood-Richardson tableau. That's why the Littlewood-Richardson rule works. So this is what I want, but I want to find out what is this set. And then once I know that set, I know this number. So I'm going for the proof before the theorem. Okay, so how are we going to try to do this? Well, Nantel and I know what insertion is in some sense. So I gave a talk on this in March. It's recorded and you can watch it on YouTube, so I won't belabor the insertion rule. I'll just try to give you the flavor of it, so you don't need to follow the details. But Here I'm taking a Conert diagram. I've left the dots in so you can read the permutation. The permutation here is 2, 1, 5, 3, 4. That's the permutation I start with. I'm going to insert, well, I need to insert a number, but that doesn't make sense because you have diagrams, not Tableau. Right? Tableau, we insert numbers because in Tableau, the boxes have numbers in them. But in Conert's diagram, you don't put, well, I do put numbers in the bubbles, but never mind that. The bubbles move, and that's your notion of the entry. It's what row is my bubble in. So here, this bubble has moved down. They're green because they're in row 3. So this bubble has moved down, so this is a Conert diagram because the bubbles move down. All right, I'm going to insert in row 1. That's like inserting a 1. My x, whatever row he's in, that's like what number I'm inserting. So here I'm going to insert a 1, and then a 1, and then a 2, and then a 2. Okay? So I insert 1 here. It comes in here and lands for magical reasons. And then I'm going to do one of those like monk moves to kind of shift things over. And then I record that I did it over here with my recording tableau. That's the lattice permutation tableau. So there's some magic here in how these boxes move, but it's worked out and it's not so bad. So then I'm going to insert again. So we'll take this guy and then I just turn this into a bubble because now I don't care that he was X and previously inserted. I just take him here and I'm going to insert another 1. And so I insert a 1 here, it lands here, and then I go here. All right, and then I turn this X into a bubble, and now I'm inserting in row 2, and then I'm inserting in row 2. So what's happening over here in the recording diagram is I'm just recording what I get. Okay, I'm recording the chain that I get from doing this. And that's the only thing that is right, is the recording tableau or the things that we should call lattice. So I thought I knew what they were, but let's look at this example. The problem comes, right here. So we have a green bubble, which means this bubble started in row 3. It got pushed down by a Conert move. Remember that top guy moved down when we were looking at Bruja order? So when X comes and lands, X lands here on these dots, and it turns that green bubble blue. It makes that bubble now tied to row 2 when it used to be tied to row 3. There was a bubble up here in this, there's this bubble in this row that gets pushed down. And when that happens, things go further to the right than they should have. And so it looks like you don't get the lattice condition, but you really do because you should really be thinking about that too as happening where that bubble is in some sense. And can I say that correctly? Clearly not. But the insertion does work. And so, okay, let's just cheat. Something's lattice if it comes up as an insertion, as a recording tableau when you have an insertion word. And what's an insertion word? So you could just insert any word you want, okay? But you're going to get garbage. In RSK, I can take any word that's Knuth equivalent, and I get the same thing. That doesn't happen here. Maybe it does, and I just don't know what Knuth equivalence is. But certainly if you take Knuth equivalent word for the tableau, you just get weird and wacky stuff. You have to take this word if you wanted to do this tableau. This is the word, so that if you do RSK insertion, I do everything backward. For a good reason here, you have to do reverse tableau because they're much more natural in this setting. They make more sense in the flag setting. So I reverse insert. So when I insert the 2, so I guess I could do the insertion. So if I was going to insert, I've got a 2, and I just insert it, and now I get a box. There's my first box. And now a 2 lands beside it. That is unambiguous. The 1, well, I want weakly decreasing and strictly decreasing. So that would be a 1, so that's my third box. Now what's next? A 4. So the 4 comes in and bumps the 2. So now 4 bumps the 2. And now I've just added a box here. And next is a 3. 3 will bump this 2. So I've added a box here. And then 2 will bump the 1. So I've added a box here. And now the 4 just comes barreling down, and it bumps this 3, which bumps that 2. And so we end up with 4, 4, 2, 3, 2, 2, 1. And we've added a 7, and there's a good chance I did it right. Yes. So that's the word I have to insert if I'm going to multiply by a tableau. I don't get to choose. And maybe you can choose. You can't choose as freely as it seems like you maybe should have. But I don't know any other word to choose. You have to do this one. So then, what is lattice? A lattice permutation tableau is anything you get where you've inserted an insertion word for any tableau. There should be a better. This is not an okay definition. It's correct, but I agree, it's not okay. And I keep trying to make it right. And now I've given up and we've switched places. So now Nantel's working on the rule and we just check it on a bunch of examples and then fix it every time it's broken. And so far we're up to n equals 7. And when we get it right, we will put the SAGE code out there and tell everyone. But we are honing in on it, and it's the number of ways we're saying it wrong is shrinking. So I believe it's converging, but we'll see. So here's another example. Here, k is 3. That's what I drew this bold line for, is just to let you know what k is. K is 3. The permutation I've written here for you, but I've done the bubbles, and so I've colored the bubbles in my lovely way of coloring things. Credit to Adelie for that. Here are all the insertion words that you get for this partition. This is S22 and 3 variables. So there are 6 semi-standard Young tableaux, so there are 6 P's. There's only 1 Q you're going for, so these are the insertion words. If you do this insertion, there are 20 Conert diagrams, exercise for the reader. There are 20 Conert diagrams. Those are pretty easy to compute. There are 6 of these, and there are 120 Conert diagrams of all these shapes together. And if anyone would really like to see it, I'll happily show you. I have this example worked out in detail on paper, well, electronic paper, all 120 cases of the insertion. And it does most of the weird things that can happen. There's like 1 or 2 weird things that can happen that you don't see in this example, but it's a pretty good example for that. You don't get multiplicity, but that's just a coincidence. And here I've written in gray what the decorations are to see the descent. So these all have weight 2, 2, which they should have. And these are the lattice guys in this case. I'm going to point out some weirdness. They all look lattice to me, except this one you have to stop and think. And here it's like, oh, well, this one stole these 2 bubbles. So really you read that one over here, so then it's lattice. And those are the sorts of things that we have to say correctly, right? It's because this one stole these bubbles because they're yellow, so they should have been in row 4, but the one stole them, and now they're in row 3. So that adjusts where we have to read it if we were going to get a reading word and just check the lattice condition on that reading word. Okay, so just to show you, here are the 9 ones that we got. And here are some things that are weight 2, 2 that you don't get. Here are the non-examples. So it's interesting here. Look, they're the same permutation, but they're different chains that can get you there. Interestingly, I like this this one, because it's a different configuration of boxes, right? The configuration of boxes just tells me there's a different subword I could have taken. So these guys are not lattice. And this one over here is really, really not lattice. At least these guys show up in some other way with a different chain, but this one, you don't even get that chain. This guy belongs into something of weight 3, 1. So these top ones are good, the bottom ones are bad. What's the rule? Well, literally what we do is Nantel sends me an example and gives me a bunch of chains and says, can you reverse these? And then I say yes or no. And can you reverse the insertion? If yes, it's lattice. If no, it's not lattice. That is not a satisfying formula, I agree, but that's what we're working with right now. But I do think that we are closing in on something that's correct. Yeah. Me too. Right. Sorry, so insertion is a bijection, okay? And there's an insertion tableau and a recording tableau. And so what you do is you say, hey, is this a recording tableau? So what I do is I say, okay, pretend this is a recording tableau. Now pick a Conert diagram for it. You might as well just take the diagram itself. But if you wanted, you could get more clever. But you take this diagram, and this tells you specifically, it's a recording tableau. It tells you how to reverse. So then you just invert the algorithm. And it breaks on all of these. These are not recording tableau. You would never get them from an insertion word. And that's what we're checking. It's like you try to reverse it and it breaks. And it breaks in like one of 2 ways. Either it's like completely hopeless, you can't do this, or it breaks because it gives you a non-insertion word. And those are the 2 ways it can break. So when it breaks, it's not a recording tableau. And that's the test. So it's not that we have to insert everything and check everything. We could just start with one of these and try to reverse it. So it's a little more efficient, but it's still not a satisfying rule. That's a clear statement of the problem. Yes, Frank. So, well, okay, I could argue we do know how to characterize them. Can you reverse the insertion? And currently it does, because unfortunately, and that's the thing, so I'm sort of sweeping under the rug here. So the insertion is intractable because the insertion says, take this diagram and consider all possible ways to give it a semi-proper labeling. Okay, so I haven't told you what that is, but there's a crap ton of them. And then if there is one that has some nice property, then you can do something. And you do that at every step you want to move a particle left. So we have coded it. I can do it faster by hand by several orders of magnitude, unfortunately, than the computer can, because it's probably, I didn't code it as well as Axel Kohnert can. So if you guys ever multiply Schubert polynomials, you're using Axel Kohnert's code that he wrote in C++ in the 80s. It's wickedly efficient. It uses Lascaux's transition formula, and that's what Sage calls out to. So by the way, kudos to Kohnert for giving us that ability to compute. I don't know an efficient way to generate all of the semi-proper labelings. So I have to do it in the most inefficient way possible because I don't know another way to do it. So there's so much new combinatorics here that we have not fully developed that I can't code it efficiently. It is codable. I could train anybody how to do it. The question is, can you do it in reasonable time? And no. I mean, what's the input? I'm not a complexity theory person. All I know is that to get it to run a single reverse insertion on something of this takes several minutes. Like several minutes on these small examples. So yes, because I know which semi-proper labeling to pick. You have to know there exists a semi-proper labeling. I can find it really fast. The computer has to run through all the possibilities and just check. So again, if you're a better coder than me, then maybe we could use machine learning to do this faster. Okay, but like in the end, or I could just try to help Nantel and come up with a characterization, which is what I'd rather do than work on coding it. So that's the problem. Can you find a way to just look at these and tell without doing reverse insertion? Maybe. We'll try. So I think there's only one more slide. Maybe there's two. Okay, so I get a lot of grief for being overly optimistic. But you know what? I'm an optimist. I don't really care. So what's the point of this if it's this hard just to get this case of multiplying a Schubert times a Schur? Because our insertion has no idea that you're inserting a Schur polynomial. Our insertion knows that you're inserting a number, which is a bubble in a specific row. It doesn't care that you're trying to multiply by a Schur polynomial. It really doesn't. So let me just do some wild speculation. I'm going to define this vector k associated to any permutation. Okay? This is my k vector. How do I get it? Well, here's the picture that it goes with. Okay? You take any bubble and you look up and you say, okay, what's the first empty row above me here? Take one less, and that's what I put, 6. So these guys all get 6s. Is that clear enough? These guys get 2 because the row above them is 2. It's empty. These guys get 4. This guy gets a 6. And then I read them like a book. It's all about finding that one example that has all the germs of generality. And the example that Frank and Nantel worked on is it, in my mind. These are the Ks that I need. Notice that if this was Grossmannian, if this was K Grossmannian, all of your Ks are K. What's this R thing? Well, I mean, this is sort of a contrivance, but there's a reason I contrive it this way. It's just put the row, R for row. What's alpha? Well, it turns out that if you take this guy and you take this guy, I can, starting from the bottom, I can peel this off by reverse inserting using this K. I can take this bubble off of this diagram. And when I do that, I get some number that I say is the end of alpha. And I do it in that specific order, and I get a word associated to any Kohnert diagram for V. Any Kohnert diagram for V, I can get a word associated. So I don't have a 2-line array. I have a 3-line array. That's what we never saw in Knuth equivalence. Knuth equivalence, or Knuth's algorithm is a 2-line array, and the top line is what I would really call this. It's sort of this thing on the board. If you made all of these, I guess for this example, these would all be 4s, these would be 3s, this would be a 2. That's the analog of what I've done up here. And it's a 3-line array. It's just the top line in the Knuth world was just all K's, and we didn't write it. But now we write it, because it's not all the same. Okay, so we take a step in the same Bruja order that Nantel and Frank were using, but now each of my steps has a different kind of constraint. It's a K Bruja step for a different value of K. And my decorations are the same decorations, but now basically they just have to match up and give me the descent set up here. They give me the descents at the right places. Okay, and okay, here's a bizarre definition, but let's just say that something's lattice if when you insert one of these specific words into a coordinate diagram, yeah, that's right. So if you insert an insertion word for V into a coordinate diagram for U, whatever you get as an output, I'm going to say that's lattice. That's a definition. There's not a theorem on this board. But that's my guess. And it's probably wrong, but I don't care. I'm happy to be wrong, because I think it's damn close. Like, I really do think it's close. In fact, it might be right. We don't know. But it gives us a place to go and look. And when you start with something that's wrong, but it's a good guess and it's kind of close, and you figure out why is it wrong, and you fix it. And maybe we're going to have to abandon it. And maybe it's not going to work. But maybe it will. And I have a lot of faith in my collaborator. I have a lot of faith in myself. We're determined, and we're making a lot of progress. And so this is what we're doing. So no, I don't think Schubert Calculus is a pipe dream. Yes, I think that the problem will be solved. I don't know if it'll be solved by me and Nantel. I don't know if it'll be solved this way. But I see no reason not to try. So that's what I'm doing. So again, what are we trying to do? I want these coefficients with no constraints on U or V. It remains an open problem. I will be very clear. It is open. We have not solved this. My guess is, hey, this bijection thing, this is this conard insertion that we've come up with. I think we're onto something. My guess is that this sum condition is the lattice condition I just told you about. It's a guess. It's not even a conjecture. It's a guess. It's a speculative, wild guess. But I think that that's exactly what you do. You have a dream and you just try it. There's no point in not trying it. And so with that, I think we can all go to lunch. Thank you.